Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am David Beams. I'm an Associate Professor Emeritus of Electrical Engineering with the University of Texas at Tyler. This is the second presentation in a series on the electrical characteristics and physics of the PN semiconductor junction. Now, Nikola Tesla did all the work in the previous presentation on the junction contact potential, so the boss gave him some time off. So we're instead going to call upon one of his colleagues as a substitute, the noted humorist Samuel Clemens, who is better known as Mark Twain. You may find it strange to learn about diodes and junctions from someone who spent his life writing humor, but it's not so strange though. I've known lots of engineers who thought they were comedians. Well, enough said. In the previous presentation, we developed an expression for the contact potential at a PN junction at equilibrium, that is, with no current flowing through the junction. Now we're going to develop an expression that describes the current that flows through the PN junction when we upset the equilibrium by connecting an external voltage source. And we will be able to describe the current for both positive and negative voltages. Let's review the principal finding from last time, that is the presentation on the contact potential. Let's take a PN junction made up of two uniformly doped N and P type blocks of material like this. This is called a step junction because of the abrupt or step change in the doping profile at the metallurgical junction where the P and N materials meet. And its contact potential is given by VO, contact potential, is KT over Q multiplied by the natural logarithm of NAND over NI squared, where N sub A is the P side acceptor doping, atoms per cubic centimeter, and D is the N side donor doping in atoms per cubic centimeter. K is Boltzmann's constant, 1.3806 times 10 to the minus 23 joules per Kelvin. T is absolute temperature in kelvins. Q is the unit electronic charge, 1.602 times 10 to the minus 19th coulombs. And N sub I is the intrinsic electron hole pair concentration of the semiconductor material in electron hole pairs per cubic centimeter. Intrinsic means undoped, pure semiconductor material. The derivation of the contact potential assumed that the junction was in equilibrium, meaning that there were no currents flowing in the junction. Now we're going to upset that equilibrium by applying an external voltage V as shown. And the potential across the junction, measured from N to P, now becomes VO minus V. But doesn't something seem wrong from this diagram? Shouldn't the junction potential be minus V? So let's clear up this point. Let's digress. The first photo below is of a 1 in 4004 silicon diode. The stripe indicates the cathode, which is connected to the N side of the junction. And the second photo is of a digital multimeter, which is set to read voltage. And its leads are open circuited and it's reading 0. This is just a functional check of the digital multimeter. The third photo is of the diode now connected to the DMM leads, and the diode is set to its diode test function. In the diode test function, the digital multimeter uses a current source and forces a current to flow through what's connected to its leads and reads the voltage across them. The reading shows that the diode is connected and it's functioning. We would expect a reading somewhere around maybe 500 some, 600 some millivolts for a silicon diode at room temperature. Now we change the digital multimeter to read voltage and it reads 0 volts. Wouldn't we expect it to read the contact potential, or actually minus the contact potential? The reason we don't is that two additional contact potentials form where the diode's leads contact the semiconductor materials, and the sum of these new contact potentials is minus VO. We're going to adopt the geometry shown here on the left, and we're going to show equations for junction potential in terms of hole and electron concentrations on either side of the junction. If we force a change in the potential at the junction, we will change the carrier concentrations at the junction. So VO minus V is KT over Q times the natural logarithm of the hole concentration on the P side to the hole concentration on the N side. And that's also equal to KT over Q times the electron concentration on the N side divided by the electron concentration on the P side. Reducing the barrier at the junction, applying a voltage that opposes the contact potential, results in injection of minority carriers, electrons into the P side, and holes into the N side. Now, I have not used this terminology before, but you might consider that if holes on the N side are minority carriers and electrons on the P side are minority carriers, then holes on the P side would be majority carriers and electrons on the N side would also be majority carriers. We expect these minority carriers, once they're injected, to move by diffusion, and we will assume that injection does not change the majority carrier concentrations. This is what's known as the low-level injection assumption. So let's go back to this equation. VO minus V is equal to KT over Q times the natural logarithm of the majority carrier concentrations of holes on one side of the junction, evaluated just outside of the depletion region, to the minority carrier concentration of holes evaluated at x prime equals 0, that is just outside of the depletion region in the N side. And that's also equal to KT over Q times the natural logarithm of the majority carrier concentration of electrons evaluated x prime equals 0 to the minority carrier concentration of electrons evaluated x equals 0. And invoking the low-level injection assumption, the injection of holes onto the N side will have negligible effect on the majority carrier concentration. So the majority carrier concentration of electrons, N sub N, is still the N side doping density, N sub D. Similarly, we will assume that the majority hole carrier concentration is simply equal to N sub A. That is the acceptor doping on the P side. So let's write an expression for the minority carrier concentration of holes, P sub N at x prime equals 0. We can write this in terms of the background concentration, which is Ni squared over Nd, plus an injection term, which we don't know yet, but we will determine. That's delta Pn. That's the injected concentration of holes at x prime equals 0. Similarly, we can describe the minority carrier electron concentration at x equals 0 as the background concentration, Ni squared over N sub A, plus an injection concentration, delta Np. We need to know both delta Pn, concentration of injected holes on the N side, and delta Np, the concentration of injected electrons on the P side, in order to find the junction currents. We'll see how that works. But let's start with finding delta Pn. So let's take this equation. VO minus V is KT over Q times the natural logarithm of Na divided by Ni squared over Nd plus delta Pn. Now, let's multiply both sides by -1. That reverses the order of the operands on the left side, and I can negate the expression on the right side by inverting the argument to the natural logarithm function. So now, let's multiply both sides here by Q over KT, then exponentiate, and then multiply both sides by N sub A, and we get this expression, N sub A e to the QV over KT e to the minus QVO over KT equals Ni squared plus delta Pn. So we're getting there. This is the term we want. We have to figure out how to get rid of this on the right-hand side. So let's move on. But VO, remember, is KT over Q times the natural logarithm of NAND over Ni squared, or minus VO is KT over Q times the natural logarithm of Ni squared over NAND. Now, let's substitute this in that expression. E to the minus QVO over KT is equal to E to the Q over KT times KT over Q, natural logarithm of Ni squared over NAND. And from that, we arrive at this. E to the minus QV over KT is Ni squared over NAND. That is very convenient because let's substitute that for E to the minus QV over KT. And then we can see, we can cancel the n's of a's on the right-hand side, and we're left with a term of Ni squared over ND on both sides of the equation. So we can find delta Pn as Ni squared over Nd times the quantity E to the QV over KT minus 1. So there we have the whole injection concentration into the N side. An electron injection under forward bias, the math is the same. Similar algebra gives us delta NP as Ni squared over Na times the quantity E to the QV over KT minus 1. And Mark Twain thinks, I thought you, Tesla, were sitting out this presentation, and Tesla says it looked like to me like you could use the help. And Twain says, thanks, but I got this. So holes are injected into the N region and they're going to diffuse left. These holes carry a current IP of X prime to the left, but they also recombine as they move. So the concentration of ejected holes is decreasing exponentially as we move further to the left with a characteristic length L sub P. Okay. So the profile of the injected hole concentration is delta Pn e to the minus X prime over LP. We have a flux of holes diffusing down the concentration gradient moving left, which carries a current flowing to the left. But the current IP of X prime is greatest at X equals 0. It decreases as X prime increases. But the electric current at in any cross section of this N region is constant. Why and how? Well, Kirchhoff's current law is Y, and electrons moving to the right to replace those lost to recombination is how. As recombination takes place, there are fewer and fewer holes diffusing to the right. There are fewer and fewer holes carrying electric current to the right, but they are being replaced by electrons that replace the electrons which were lost to recombination that are moving to the right, and a negative charge moving to the right, a positive charge moving to the left, both contribute to electric current flowing to the left. So if we can find IP of X prime equals 0, the current carried by injected holes at X prime equals 0, we will have the electric current that's flowing through the entire junction due to the injection of holes. And we can find the total flux of holes at X prime equals 0 from the junction area, the hole diffusivity dP, and the slope of the hole concentration. In other words, the hole concentration gradient at X prime equals 0. So the total flux of holes is minus A times the diffusivity times the gradient of the hole concentration, injected hole concentration, evaluated at X prime equals 0, which gives us simply this as the total flux of holes. And the current that they're carrying is just, we find that by just multiplying by Q, the unit electronic charge. So this is the junction current that is due to hole injection. Now, electrons are injected and diffused to the right in the P side, But electrons moving right will carry a current In of X to the left. But they also recombine as they move, resulting in a concentration that decreases exponentially with a characteristic length we'll call L sub n. So the concentration of injected electrons on the p side becomes delta np e to the minus x over Ln. If we can find In at x equals 0, we will have the electric current flowing in the junction due to the injection of electrons. Thus, the flux of electrons, of injected electrons at x equals 0 is minus the area times the diffusivity of the electrons times the concentration gradient of the electrons evaluated at x equals 0. And it's straightforward to find the total flux of electrons at x equals 0. And from that, we find the total current flowing left. Remember, current is going to be flowing left, negative charges flowing to the right will produce a positive current flowing left. So here we have the current that is carried by electrons injected across the junction. So we can find the total junction current simply by adding those two components of current, the current carried by injection of electrons into the p side and the current that's carried by injection of holes into the n side. And we add them together and we come up with this expression, which is known as the Shockley diode equation. It relates the current in the junction to physical parameters of the junction and of the semiconductor material and to the applied external voltage. So at long last, we have the junction current in terms of applied voltage V. It predicts an exponential increase in I with applied voltage V. But observe now what happens if V is much less than minus KT over Q. And KT over Q has a value of 25.9 millivolts at 300 kelvins, which is slightly above room temperature. So we can say that KT over Q is about 25 millivolts at typical room temperature. So if we have a voltage, say, of minus 150 millivolts or so, then the exponential term becomes negligible compared to the minus 1, and we can ignore it. Under these circumstances, we get I is simply this expression. So if V is negative by more than a few hundred millivolts, let's say, we expect a constant current independent of the applied voltage. And what is frequently done is to take this entire expression here and call it I sub S, where I sub S is the diode saturation current, and that makes the Shockley equation simply this. I is the saturation current multiplied by the quantity e to the QV over KT minus 1. Nice. Well, here is the I versus V curve for voltages from 0 up to about 700 millivolts or so for a 1N4148 silicon diode. And it certainly does look like an exponential increase in current with applied voltage. Here we have a curve from a gallium arsenide phosphide red light emitting diode, and it also shows what appears to be an exponential-like behavior. So Tesla has jumped in here, and Twain says, yes, I agree, they do show exponential IV relationships, but did anyone ask for your opinion? So real junctions are often graded junctions in which there's a gradual transition from N to P instead of an abrupt step, and they're often not of constant area. So the geometry that we had assumed is not totally realistic. A modification to the Shockley equation that gives a better representation of real junctions is to introduce a parameter eta, which is known as the emission coefficient. And modifying the Shockley diode equation with the emission coefficient makes this. I is I sub S e to the eta QV over KT minus 1. What I'm going to show you now is something I've never seen in any textbook. We can use ordinary laboratory equipment to make measurements that allow us to calculate I sub s and eta for a given junction diode. Let's start with the modified Shockley equation. Now, suppose we apply a voltage V such that the exponential term here is much greater than 1. Since KT over Q is about 25 millivolts at room temperature, applying a voltage V of about 150 millivolts or more ought to be sufficient. So now we can ignore the 1, and that gives us this simple expression: I is the saturation current times e to the eta QV over KT. Now let's take the natural logarithm of both sides of the equation. Natural log of the current equals the natural logarithm of the saturation current plus eta Q over KT times the applied voltage V. This equation takes the form of a straight line with a slope of eta Q over KT and a y-axis intercept equal to the natural logarithm of I sub s, saturation current. So what we'll do, we will plot the natural logarithm of current versus voltage. We will find a straight line that best fits these data and determine the slope and the y-axis intercept of that line. And we'll use the slope and known value of KT over Q to calculate the emission coefficient, and we'll calculate the saturation current from the y-axis intercept. Let's see how this works. There's just one detail here. We want a reasonable positive voltage, maybe 100 to 150, 200 or more millivolts, so that we can ignore the -1 term in the Shockley equation. But we also want to keep the diode current relatively low so that the effects of the resistances of the semiconductor regions are minimized. The Shockley equation derivation assumed that there was no voltage drop across the N and P regions of the junction outside of the depletion region. That, of course, is not strictly true, but if the current's kept small enough, we can assume that we can ignore the voltage drops in the bulk semiconductor material. Well, let's see how this works. Here is the natural logarithm of current versus applied voltage for a 1N270 germanium diode. And the coefficient of determination of the fitted line, it's the black dots, to the orange line, which is a plot of the actual data, is extremely good. Looks like our derivation does work in practice. Well, here's the plot of the natural logarithm of the current versus voltage for a silicon diode, a 1N4148. Coefficient of determination there is 0.9995. Pretty good. Again, the orange trace is the diode current. The black dotted line is a line fitted to the data. And here we have a plot of the natural logarithm of current versus voltage for the red light emitting diode. Again, the data that are measured fit a straight line, the straight line expectation from our derivation quite well. So let's take some numerical results from those graphs. Here I have the 3 different diodes that were measured. And here are the computed saturation currents for each of these diodes. And we have also in this column here the computed emission coefficients. An emission coefficient of around 1/2 in a graded junction is a reasonable number. So we have what look like valid, not outlandish results. And let's take a look at this. The saturation current of the germanium diode is about 7.4, 7.5 microamps. The saturation current of the silicon diode is 2.29 nanoamps. And the saturation current of the red light emitting diode was about somewhere around 3.9 to 4 times 10 to the -18th amperes. Now, it would have been very difficult with ordinary laboratory equipment to have measured currents like these. But why the wide range of saturation currents? Well, let's take a look over here in this column. Now, these are not experimental data. These are data which I've gleaned from available sources. The band gap in germanium, 0.67 electron volts. In silicon, it's 1.14. Well, we would expect the intrinsic carrier concentration of silicon to be considerably less than that of germanium, and it is by a factor of around 3,000. Remember that the model predicts that the saturation current is proportional to the square of the intrinsic carrier concentration. So this large difference in saturation currents is not unexpected. But now look at this. In the gallium arsenide phosphide red light emitting diode, look at the orders of magnitude of the currents, the saturation currents. Look at the band gap of gallium arsenide phosphide material. Now, gallium arsenide phosphide is actually a mixture of gallium arsenide and gallium phosphide. It's used in making light emitting diodes. The band gap of, let me back up. The color of the light emitted by a gallium arsenide phosphide diode depends upon the relative amounts of gallium arsenide and gallium phosphide. Pure gallium arsenide emits light in the infrared region, and gallium phosphide emits green light. By varying the ratio of gallium arsenide to gallium phosphide, we can adjust the band gap. The band gap energy is the energy of the emitted photons. That change in energy allows us to, or the ability to tailor the band gap allows us to tailor the color of light that's emitted from the light emitting diode. So the band gap here, 1.85, was calculated from an assumed radiation at a wavelength of 670 nanometers, which is right in the middle of the red range. And this band gap of 1.85 electron volts results from a composition of 63% gallium arsenide and 37% gallium phosphide. So the results that we obtain by these measurements appear to be consistent with known physical properties of these semiconductor materials. So this was just a test of how well did the numbers calculated for saturation current and emission coefficient match the real device. And the blue curve here is diode current versus diode voltage for a 1N270 germanium diode using the measured values of saturation current and emission coefficient. And the orange triangles represent the actual measured data. Seems like a reasonably good fit. So we think we're on pretty good both experimental and theoretical grounds here. Well, we can see that the experimental results do confirm the predictions of the Shockley equation despite the simplifications built into the model from which it was derived. So you now have a basic understanding of the solid state physics of the PN junction that will be useful in understanding other electronic devices. And Nicola comes back and says, let's give it up for our guest presenter. He did a fabulous job, especially considering that he never studied engineering or physics. So, and Mark Twain departs the scene, but Nicola sticks around and he says, but now that he's gone, I want to show you some practical applications or implications of the diode saturation current ISOPS. First, let's introduce the schematic symbol of the diode with reference polarities and directions for voltage and current. The two terminals of the diode are known as the anode, which is the P region, and the cathode, which is the N region. And we define the voltage across the diode as positive at the anode with respect to the cathode. and we define the current as positive if it enters the anode and leaves the cathode. So here we have an IB characteristic according to the Shockley equation. And now we're going to label the 4 quadrants of the graph, the current versus voltage graph, 1 through 4. Normally this diode would operate either in quadrant 1 with a positive voltage and a positive current, or if we apply a negative voltage, that puts the diode into either quadrants 2 or 3, but because the current is negative, when we apply a negative voltage to the diode, that means it operates in quadrant 3. But we've already seen that saturation currents are very small, so on a linear y-axis graph, they essentially appear to be 0. Now, in this quadrant with positive voltage and positive current, the diode is actually consuming or dissipating energy. It's dissipating power, the power being the voltage multiplied by the current. Now look what happens when we illuminate the junction with light. Notice the large change in the saturation current due to the generation of electron-hole pairs by absorption of photons in the vicinity of the junction. The junction now will operate in quadrant 4 if we connect it, instead of to a voltage source, to an external resistor. And in quadrant 4, where we have a positive voltage and a negative current, the diode is now an energy source. It's transforming optical energy into electrical energy and delivering it to the load. This is the basic principle of the photovoltaic cell, or what used to be known as the solar cell. The junction can also be used as an optically controlled current source. If we place the diode in a circuit that holds the voltage across the diode at 0 volts, and we detect the change in I sub S. We can detect when the diode is illuminated and when it's not. The so-called photodiode is an important device in data communication, instrumentation systems, and power electronics. I doubt if Mark knew that. He's a smart guy, but he just isn't an engineer. But for now, zdravo, which is Serbo-Croatian for bye and see you later. So, appreciate your watching, and we'll see you in the next presentation.